In this video today, we're going to do a Scikit-Learn crash course. What this means is we're going to learn how to use Scikit-Learn as a toolkit. This is a toolkit that you use for traditional machine learning, for stuff like regression, classification, clustering, PCA, without neural networks, so without using deep learning. This is for traditional methods, so k-nearest neighbors, linear regression, support vector machines, random forest classifiers, and so on. But I want to mention that this video here is not going to be a machine learning crash course. It's going to be a Scikit-Learn crash course, which means we're not going to discuss the individual methods. We're not going to go deep into regression, into k-nearest neighbors, support vector machines. We're not going to discuss the methods and how they work. We're going to discuss Scikit-Learn as a toolkit, which means we're going to go through the full process of using a data set, doing a train test split, doing maybe a different sort of split, pre-processing the data, training classifiers, training regression models, doing clustering, doing dimensionality reduction, and so on, doing some visualizations, also evaluating the models, doing hyperparameter tuning, building pipelines. So we're going to focus on Scikit-Learn as a toolkit, and of course we're going to touch on machine learning concepts, but this is a Scikit-Learn tutorial, not a machine learning crash course. This is important to know. Also, you do need to have some prerequisites here. You should be comfortable coding in Python. You should be somewhat comfortable with NumPy, Pandas, and Matplotlib, because these are libraries that we're going to use in addition to Scikit-Learn just because they belong together. You cannot work with data sets if you don't have data frames. You cannot train models on data if the data is in NumPy format and you don't know what NumPy is. So yeah, these are some things that you need to know in advance. Besides that, we're going to cover everything for beginners. So let us get right into it. All right, so let us get started. The first thing we want to do is we want to set up our environment, which means we want to install all the packages that we need for this video today, and we want to choose a development environment. Now, in my case, I have a directory called tutorial, which is where I'm going to do all the work. And in here, I'm going to set up everything using UV, which is personally my preferred package manager. However, you don't have to use it. You can use pip. You can create virtual environments with venv or virtual env. That's completely up to you. The important thing is that you get the packages installed on your system. How you do that is completely up to you. The default way is you want to say pip or pip3 install. And then we're going to need in this video today, obviously, Scikit-Learn, NumPy, Pandas, and Matplotlib. These are the packages. Scikit-Learn, obviously, for the machine learning stuff, NumPy for working with arrays, Pandas for working with data frames. Some of the data sets come as data frames, and Matplotlib for the visualization. So that is the basic way, the default way to install packages. Of course, what you can also do is you can say Python or Python3 -m venv.venv. This will create a virtual environment. Then you can activate it and work like this if you want to. What I'm going to do is I'm going to use UV. So I'm going to use this package manager UV, which is just faster. It's Rust-based. So in my case, what I do, and if you want to do the same thing, you need to first install UV. I have a video on this channel if you're interested in that, but you don't need to follow along with that. UV init is how I create it. And then I say UV add Scikit-Learn, NumPy, Pandas, and Matplotlib. This is just how I do it. In addition to that, I'm going to install JupyterLab. JupyterLab is a way to work with interactive Python notebooks. It's just a development environment in the browser. And the reason we want to work with IPython notebooks instead of just ordinary Python files when it comes to machine learning is that we want to run individual cells. So loading the data set, then maybe exploring it, playing around with it, doing some transformations, training a model, evaluating a model. We don't want to do this in one big code file and then just run it from top to bottom every time we change something. We want to be able to change individual parts of the code, rerun individual parts of the code, and so on, without having to retrain and reevaluate the model every time we make a small change. So that's the reason we want to work with interactive Python notebooks. Because of that, I'm going to install JupyterLab. Once we have this done, or once I have this done, I'm going to say venv bin activate, and before that I'm going to say source. So that is going to activate the virtual environment. And now I'm going to just say JupyterLab like this. This is going to open up my browser with a JupyterLab instance. Let me just put my terminal here to a different workspace. And now we have this setup here. So we have some files that are not important to us right now. And here I can now just create a simple IPython notebook. I can store this and I can call this main or something. And here now the idea is quite simple. For those of you who don't know interactive Python notebooks, I can run some command here, for example, print 10. Then I can run something else here, for example, x is 20 as an individual cell. Then I can say print x. Then I can go up here and I can say x is 10. Then I can run print x again. Now it's 10. And I can, of course, also have multiple things here in the same cell. But the idea is I can run cells individually. I can rearrange them and all that. This is just way more convenient when we do machine learning or data science work. So what I want to do here first is I want to give you one example, a very, very basic Hello World-like example of training a model and evaluating a model on a data set in Scikit-Learn, just so you see what the basic idea of using Scikit-Learn is. And then I want to go more into the details. First of all, we're going to talk about how to use data sets. Then we're going to talk about splitting data and doing something like a train test split or a stratified shuffle split. We're going to then talk about pre-processing, stuff like scaling, stuff like encoding. Then we're going to talk about classification, followed by regression, followed by unsupervised methods like clustering and PCA. Then we're going to talk about evaluation with different metrics. Then we're going to look at cross-validation. After that, we're going to do hyperparameter tuning. And in the end, we're going to talk about pipelines. That's the rough plan for today. But I want to start with an example that is going to already use a bunch of these concepts before we have talked about them, just to give you a basic idea of what it is we're doing with Scikit-Learn in general. So what I'm going to do is I'm going to train a simple classification model to recognize or to classify, to detect, you could say, breast cancer. So for this, we're going to say from Scikit-Learn.datasets. This is the datasets module here. I can import the load breast cancer function. This is a function that loads a dataset. Then I'm going to say from Scikit-Learn.model selection, I'm going to import a train test split. This is a function that allows me to split the data into a training portion and into a testing portion. Then I'm going to say from Scikit-Learn.preprocessing, import standard scaler. This is, as the name already says, for scaling the data, which is important, very important for certain algorithms because they are scale sensitive. And then we're going to say from Scikit-Learn.neighbors, import kneighbors classifier. So this is one specific type of classifier. I'm going to mention when we talk about the classifiers roughly how they work. Right now, just accept that this is some algorithm that learns from data and then makes predictions. In this case, prediction would be, is this thing that we're looking at a cancer? Yes or no? Is it malignant or benign? Is the proper classification? And we're just doing these imports now, and we can start by loading some data. So let's say X and Y, X being the features meaning we have certain attributes of a cancer or of a cell or whatever we're looking at, a tumor, I think. So actually, before I do the XY split, let's go and say data is equal to load breast cancer. And maybe also load it as a data frame so we can take a look at it like this. So here you can see what this looks like. We have some stuff like radius and texture and perimeter and area and smoothness and compactness. So attributes that describe the tumor. And then we have the final classification on the very right, which is the target. Is it malignant or benign? Now, to be honest, I'm not sure if 0 is, I think 0 should be benign and 1 should be malignant, meaning 1 is a positive case, tested positive for cancer, I think. So that's the data set. And when we do an XY split, so if I say X and Y, load breast cancer, here I have to provide return XY equals true. Then we don't need the frame. And then this is going to be split into X, which is a NumPy array, a multi-dimensional NumPy array with all the feature values without the labels, without names anymore. And Y is the target. So Y is what we're trying to predict. Is it 0 or 1? That is the format that we need for Scikit-Learn in general. And this is also what we get by default from the datasets module. Now, when we have that, we can split that into training and testing data. So now I can say xtrain, xtest, ytrain, ytest is equal to a train test split of x and y with a test size of 0.2. Again, we're going to talk about all these things in more detail. I'm not going to do it yet. I just want to explain to you what we roughly do here in Scikit-Learn, and then we're going to talk about loading stuff and fetching stuff and returning differently in a second. Then we're going to talk about splitting and doing train test splits in a second as well. For now, just accept this function takes the data we have here and splits it into training and testing data. Now we can also scale the data. So I'm going to say scalar is equal to standard scalar, also something we're going to discuss in more detail in this video. But for now, let's just say x train scaled is equal to scalar dot fit transform. We're going to transform x train. Now we're going to do also the same thing with the testing data, but just with the transform function. I'm going to also explain why we do this. And now we have our training and test x data scaled properly. So we have scaled it with the standard scalar. And now easily we can just go ahead and say k nearest neighbors is equal to a k neighbors classifier. And then we can fit that classifier on the training data. So we provide the scaled x data and we also give it the ground truth. So what should it predict based on this data, the y train data. This results in our k-neighbors classifier being returned. And now we can go ahead and see how well it scores on unseen data. So I can say k&n score, and I can run it on the test data and see that it makes 95.61% correct classifications. And of course, if I now have a new instance, I would just have to go and say k&n predict and provide a new instance here manually as an array. And I would get a classification 0 or 1. That is the basic principle here. This is how it works. And this is what we basically use Scikit-Learn for. We have a data set. We either want to do classification or regression, or we want to do some clustering. We have some data. We want to train on that data, and we then want to make predictions with our trained model. In this case, we have a breast cancer data set. We load it. We split it into a training and a testing set. We scale the data. We train a model, and then we see how well the model performs on unseen data. This is the rough overview of what we do with Scikit-Learn. Of course, a lot more stuff can be done here. We can do more evaluation. We can do hyperparameter tuning. We can do more preprocessing. We can load different types of data. But that is the basic workflow. So now I want to get started by talking about the Datasets module and how to work with datasets in Scikit-Learn. For this, let us remove all of that. We don't need to talk about this yet. We're just going to import from sklearn datasets load breast cancer. I'm going to also remove all these cells. And now I'm going to say load breast cancer like this. So this is the default way to use the function. You just call it and you get something in return. We can also save that into a data variable, and then we can show the content of this data variable. So if we just use the function, this is a classification data set. If we just use the function, we get a dictionary with data and some array data here. So these are the features. We have 30 different features and 569 instances. So 569 individual instances of tumors and 30 different features to evaluate these tumors. And then we have a target, which is either true or false, either malignant or benign. We can also see here the target names are malignant, benign. Actually, it seems like 0 is malignant and 1 is benign because of the order here. So this would be malignant, this would be benign. So it was the other way around, not the way I said. This is what you see here in target names. I think we should also have feature names somewhere. This is not the best overview. There you go. Feature names is an array of mean radius, mean texture, mean perimeter, and so on. These are the features that we use to determine whether a tumor is malignant or benign. Then we have some metadata here like the file name and the data module and so on. We also have a description. Where does it start? There you go. Description here, which summarizes the data set, but that is what you get by default. Now you can of course keep it like that and then do your own split by saying x is equal to data.data and y is equal to data.target. And then you basically have the same thing that we had before. We have y and x, or x and y as arrays. But if you want to do that and you don't need any of the other information, for example, the feature names or anything like that, you can just go and return xy immediately. So you can pass a parameter here that says return xy equals true. The result of that is that you're now going to get a tuple, or you're going to get two values, x and y. So instead of storing that in data, you can just say x and y is equal to that. And now you can just see what you get as a result is x and y the way we had it before, if you prefer this format. Also, as we saw, you can export you can import as a pandas data frame. So you can just say in here as frame equals true. But if you do that, you want to also get the frame. So you want to say dot frame. And you only need a single variable. Let's call it df. And then if I say df, we can see that this is a pandas data frame. So we can see we have the columns here, we have the values, and that is a different data format. And this is possible for all the data sets that we see here in Scikit-Learn. We also have regression data sets. Another one here would be fetch California housing. Now there's a difference between load and fetch. Load means loading it from the package itself. Fetch means loading it from the internet, so you're actually downloading the data set. But the California housing data set, for example, would be one of the regression data sets. So we can take a look at that. Let's say df2 is equal to fetch California housing as frame equals true dot frame. And then let's take a look at df2. You can see we have here the median income, the house age, average rooms, and so on. And then the target variable, the median house value. So this is what we're trying to predict. This is a number, not a classification. Because of that, it's a regression task. We're trying to predict a value on a continuous spectrum, not just a discrete class or label. This is why it's a regression data set. And the whole exploration of the data set now is not really something you do with Scikit-Learn. It's more something you do with Pandas itself. And I do have a Pandas crash course on this channel already, so I'm not going to spend too much time explaining that. But basically, you have this data frame, and now you would do something in the case of the first one like df.histogram. And then maybe we want to also import matplotlib.pyplot as plt, just to have a tight layout. And then we would get a histogram of all the individual features. Now this is quite small. Let me maybe go with a figure size of something like 14.8. There you go. So now we have the individual features and their distribution. A lot of them are normally distributed, at least somewhat. Some of them see more like a Poisson distribution, if that's how it's pronounced, not sure. But you can take a look at the data. You can do some visualization stuff. You can use methods like, describe. You can use info, and so on and so forth. This is more like Panda stuff, so I'm not going to cover this too much. Of course, same thing works for the regression data set. Just plot a histogram. Then you have the distribution here. Again, you can increase the figure size, do tight layout to have a better visualization here. So yeah, one way to work with datasets in Scikit-Learn is to load them directly with scikit-learn.datasets. Of course, you don't have to do that. You can do the same thing with just pandas. Get a CSV file from Kaggle, load it with pandas, and then you can do the same thing with Scikit-Learn as well. So you can still train models, do evaluations and everything. This is just a convenient way if you need some toy datasets or something to play around with, something to try stuff out. You can just use Scikit-Learn datasets. However, you do also have stuff like, I think it was fetch OpenML, I think, yeah. In this function, you can provide also specific data sets like Titanic or car data sets. So you have a string that you can provide. We're going to take a look at that later on in the tutorial. I'm going to use some of the data sets from here. But basically, this allows you to have more than just one data set per function that you use here. So you do have quite a bit of choice here. And one of the coolest things, I think, especially for proof of concepts, is to use the make functions. So we also have functions called make blob, make moon, and so on. Basic idea being I can say from scikit-learn.datasets import make, and you can see we have a bunch of make functions here. Let's go with blobs. And what this does is it generates randomly data according to certain you could say distributions or structures. So make blobs, for example, as the name says, creates clusters. So clusters of data points. We can take a look at that. I can say, for example, x and y is equal to make blobs. Then I can say I'm interested in having 5,000 instances and 5 blob centers. So 5 clusters essentially. Then I get my data set. We can take a look at it again. I have my data 2-dimensional by default, so 2 features. I can also increase that by saying number of features is equal to, for example, 5. That would make my data 5-dimensional, but for the sake of visualization, let's keep it as at 2. So I have now 5,000 instances with 2 features, and I also have the corresponding classes. So I have 5 different classes since I provided 5 as the centers keyword argument. And now I can easily just go and say plt scatter, take my data, everything, every instance, 0th or 1st dimension, then every instance, 2nd dimension, and then I can say the color is equal to y, to the labels. And this is what it looks like. Now, this is my artificially created data set. I can also rerun this since it's random. I'm going to get a slightly different data set. There you go, or a significantly different data set. These two are a little bit merged, so they're not really separate clusters. So maybe it's difficult to recognize them as 2 separate clusters. But you get the idea. So I can rerun this a couple of times and also specify a different number of samples. For example, maybe 500. This is much less data here. So this is what this looks like. And you can play around with that. We also have different methods like, let me just collapse this here briefly. We also have stuff like make moon or make moons. What was it called? Make moons. And what this does essentially is it gives us a certain shape. So let's leave it at the default. This gives us a data set like this. We can also add some noise. So I can say noise is equal to 0.8 to make it a bit more chaotic. This is a bit too chaotic. Let's go with 0.3. Still very chaotic. Let's go with 1. There you go. So now you can see the pattern is the same, but there's a little bit more noise. This can be useful to play around with different clustering methods, for example. So if I don't have the labels, something like k-means clustering would probably do a 50-50 split here, whereas something like dbScan is able to recognize this curved structure here by just working with proximity and neighborhoods. But we're going to talk about this when we get to clustering. The important thing for you to understand in this section of the course is we have the datasets module. We can load datasets that are provided by Scikit-Learn on your system automatically. These are the load functions. We have fetch functions that allow you to pull datasets from the internet. And we have make functions which allow you to randomly generate data with Scikit-Learn to play around with. One more thing, maybe if you want to have a determined generation. So if you want to have the same consistent generation every time, you can provide something that is referred to as a random state. It's a seed essentially. If I provide, for example, 0 here, this will always be the same generation. So I will always get, let me maybe just delete these cells here so we can see that more easily. We will always get the same data set. No matter how many times I run this, it's going to stay the same. If I provide 1, I'm going to get a different data set. But again, always the same. It's not going to change. If I don't provide a random state, I'm going to get a different one every time. So then it's going to be random. Every time I run this, it's going to be a different data set, slightly different data set. So if you want to have persistence, if you want to have the same consistent generation, you have to provide a random state, 42, and then you get the same generation every single time. So yeah, that's it for the data sets. Let us now move on to the next concept. And the next concept that we're going to talk about is the concept of splitting the data. So let us load now a different data set from Scikit-Learn.datasets. We're going to load the iris data set. This is basically a flower classification data set. And in addition to that, we're going to load from Scikit-Learn.model selection the function train test split, which we already used in the introduction example. And now we can do the basic stuff as before. X and Y is equal to load iris, return X, Y true. And basically this data set gives us 4 features per instance. And we have also 3 different classes. You can see it's not a very large data set. Maybe if you want to just load iris, you can also take a look at the description and the feature names. So the feature names here are some length, some width, some other length, and some other width, basically just dimensions of the flower. And then we also have the target names, which are 3 different flower types. So that is the data set that we're working with here. And what we usually do in machine learning is we train a model and we evaluate a model on different data. It doesn't make sense if I teach you something based on data. If I give you some examples, let's say I want to teach you, for example, what a cat looks like versus what a dog looks like. And maybe you've never seen these two animals. If I show you some pictures of cats and dogs and you train to recognize cats and dogs based on these pictures, then you performing well on these pictures doesn't necessarily mean that you understood what cats are and what dogs are. Maybe you just memorized these pictures and you understood, okay, this one is a cat, this one is a dog, but you didn't generalize. You don't understand the features of a cat or of a dog. You just recognize the pictures that you already saw. And because of that, you perform very well on the training set. But if I show you pictures that you've never seen before, maybe you fail completely because you're not able to generalize. This is the problem of overfitting. If you overfit your training set, you basically memorize it and maybe you don't generalize well. So what we do in machine learning is we train on one portion of the data and we evaluate on an unseen portion of the data, so on a separate portion, so that the model cannot memorize stuff. It can just learn and then generalize, hopefully, towards being also performing well on a testing data set. We then also have the concept of a validation set, which is sometimes useful if you want to tune hyperparameters, but this is something that we're not going to talk about yet. So the basic idea is we want to split our data, the full data that we have, into a training set and a testing set. And we can do that in different ways. Now, the basic way is to just do a random split using the train test split method or function. So what I would do in this case is I would do train test split X and Y, and then I need to provide a test size and a train size, which is implicit. You know, if you provide one, you have the other one. But if I say now here, for example, test size is 0.2, what this means is 20% is going to be used for testing and 80% of the data is going to be used for training, which in our case means this is what I get as a split. We're going to talk about this in a second. But in our case, this means I have 150 instances, 150 examples. So if I now say 0.2 times 150, I would take 30 instances and not train on these 30 instances. And I would only train on the remaining 120 instances and then evaluate my model, see how well the model performs on the remaining 20%, so on the remaining 30 instances. So how we get the data as a result of calling train test split is we get first the training data X, or the X training data, then we get the X testing data, then we get the Y training data, so the labels, and then we get the Y testing data. That is what we get as a result here from train test split. So if I say length X train, you can see 120 instances, X test 30 instances. So yeah, and these are not the first 120 and the last 30. This is a random split. This is a train test split that is completely random, which is not necessarily optimal. And we can see that this is the case by using NumPy and Matplotlib to visualize something. So if I say here, import NumPy as NP and import matplotlib.pyplot as PLT, I can do a visualization. I can see what is the distribution of the classifications, of the labels. So is it equal? Is it very different? Because the problem is if I have a training set where, let's say, one or two classes are disproportionately present, whereas one of the classes is not present at all, or only a few instances are in the training set, and in the testing set, it's completely flipped, so it's completely the opposite, then of course I cannot really say that my evaluation is very meaningful because I'm working with very different data sets. So I can say counts is equal to np bin count y train. Then I can say positions is equal to np a range 3. And then I can say plt bar, and I can say positions counts. And then I can say plt xticks positions. And for this, I would have to load the data separately. So let's maybe do something else. Let's say data is equal to load iris like this. And then let's say x and y is equal to data target. The rest stays the same. But what I can do now here is I can say data dot target names. And when I do that, in this case, it's not that bad. So we have a roughly a somewhat balanced distribution here. But if I run this a couple of times, probably we're going to get a different split, maybe an unbalanced split. It doesn't have to happen every time, but it happens sometimes. And that is enough if you get a bad split to end up with something where you have a skewed data set. So yeah, this is not the most extreme example, but you can see in the training data set, we have many instances of the third class and not so many instances of the second class. Now, if I copy that and if I do the same thing for the testing data, this is probably going to be flipped in the case of this data set. So if I say y test, you can see that this is now exactly the opposite. I have way more of this class than of the other two classes. And if I train on this and evaluate on this, this might lead to problems, and maybe my evaluation is not really perfect in this case. So it makes much more sense to have a somewhat equal distribution here when it comes to the classes in the training data set and in the evaluation data set. And for this, we can use something from Scikit-Learn called a stratified shuffle split. So I can say from sklearn.model selection import stratified shuffle split. And what this does is it guarantees, or it pays attention to having a similar distribution. So to having the same ratio of the different classes in the training and the testing data set. How can we do that? We can define a split. This is a class, so we need to create an instance of it. So stratified shuffle split, n splits is equal to 1. We only need a single split. The test size is 0.2. And now what I can do is I can say for training index, testing index in this split. So in split.split, x and y. Now I can access the indices. Indices just means we select indices from the set to assign training or testing data to them. And then I can just say xtrain and xtest is equal to x train index, x test index. And then I can do the same thing with y and y and y and y. So if I do that, now we can take a look at the same visualization. I can run the cells from above. Now we have a new y train. So now I have a perfectly balanced training data set. And if I do the same thing for the testing data set, I have a perfectly balanced testing data set. This is what you can achieve with a stratified shuffle split. It's not always necessary, but it can make sense to do that. Sometimes a train test split for the sake of simplicity is also fine. But yeah, just so you know it exists. And of course, there are many other ways to split data. I can also show you that in the documentation. As a general rule of thumb, I would recommend you go to the documentation and you take a look at all the other stuff that is available here, because what I'm going to do in this crash course today is I'm going to show you some methods. I'm going to show you some split methods, some metrics, some pre-processing methods, but I'm not going to show you everything. And because of that, you should go into the documentation and see what else you can find here. So for example, we covered here now the stratified shuffle split, but we also have a time series split, or just a shuffle split, or a repeated k-fold cross-validator. So we have a bunch of stuff. I don't even know all of them, but we have a bunch of stuff here that you can use. You can just click on one, read what it does, and look at code samples, and then you can see if this is useful for you, or you can just look it up once you need it. Now let us move on to the pre-processing. Pre-processing is a quite comprehensive topic. We have scaling, we have transforming, we have encoding, and all of this is listed here as one category, Scikit-Learn, or as one module, Scikit-Learn.preprocessing. We're of course not going to cover all of this. I just want to cover a couple of basic classes here to show you what you can do with them. But the idea of pre-processing is that you get some data and the data is not perfect to be used right away with your model. So you want to train, let's say, a k-neighbors classifier on your data, but the data is not perfect. Some of the features might not even be numerical. Some of the features might not be scaled yet. And this is important for a distance-based classification algorithm, for example. And because of that, you need to pre-process the data. You need to do some stuff with the data before it can be used for training and evaluating the model. So in this case, we use the module Scikit-Learn.preprocessing. And I want to start by talking about the standard scaler. This is something you're going to use quite often as a machine learning engineer. It basically scales the data to a specific format. Let's take a look at an example. If I have the iris data set, xy is equal to load iris, return xy equals true. We discussed that we have some lengths and widths in here, and you can see that these are in the actual units. So this is not scaled, this is not normalized or anything like that. This is just the raw centimeter values. And this can be confusing because a lot of the algorithms that we might use for classification and regression are actually based on certain distance measures. So on the Euclidean distance, for example. And that can be a problem if we're working with algorithms that are scale sensitive, for example, because they use a distance measure. As an example, the k-neighbors classifier, what it does is it asks which of the data points are closest to my new point that I'm trying to classify, what are their classes, their labels, and then just take the most common one and assign it to the new instance. The problem now is if I have one feature that lives on a spectrum from 0 to 1, so a very small scaled feature, and then I have another feature that has maybe a range from negative 2000 to positive 4000, then of course this second feature is much more important because it is much more relevant when calculating something like the Euclidean distance. So to make all features equally important, what we do is we scale them down to the same variance, so to unit variance essentially. And we can do that in different ways. We can use a standard scaler, we can use a min-max scaler, so there's different approaches to that, but the standard scaler is something that we're going to use quite often in machine learning, so we're going to take a look at this one first. So our goal is to take these features that live on a different scale. You can see this one is somewhere around 4 point something, 5 point something every time. This is 0 point something, this is 1 point something. So they have a different scale. And if we just leave it like that and we use something like a k-neighbors classifier to train on this data set, then this first feature here is going to be much more important than the last feature just because it contributes much more to the distance. So we're going to scale the data now by creating an instance of the standard scaler. And then what we do is we do a fit transform. So in order for this to make sense, let us briefly just split into training and testing data. So again, xtrain, xtest, ytrain, ytest is equal to train test split x and y with a test size of 0.2. And the reason we call fit transform is because the scaler has to learn certain values. What it does is it takes a sample, it takes the mean from the sample, and the standard deviation from the sample, or the variance, and then it does some calculations based on these values that it learned from the training data. And the reason we call fit transform on the training data is because we're learning these values and doing the calculations. So if I want to say xtrain scaled, I say this is equal to learning the values, so fit, and transforming the data. So we learn the values from the training data, we apply the scaling onto the training data. As a result, we get the trained data in a scaled way. And if we want to do the same thing with the testing data, we don't fit again. We use the learn parameters. We use the same mean and variance as before, so we just do transform. Because of course we don't know what the testing data is before we see it, so we are going to use a scaler that is trained on the training data. And now if I take a look at the scaled data, you will see that they are all roughly on the same scale, or they are on the same scale. Now, if you want to understand what is happening here, first of all, of course, you can look into the documentation, but second of all, you can just do it manually. So what we can do is we can transform, or we can scale the data set ourselves with NumPy. How do we do that? Import NumPy as NP, because what the standard scaler basically does, it subtracts the mean from the data and divides by the standard deviation. By doing this, we zero center the data and we bring it to unit variance. So what I can do here as well is I can say, give me xtrain, subtract the mean of xtrain, so NP mean xtrain. Important here, we want to specify axis equal to 0, because otherwise we're taking the mean across all these values here. But we want to do that per feature. So I don't want to subtract the mean of everything from everything. I want to subtract the mean of feature 1 from all feature 1 values, which is why I provide axis 0. So I do this calculation, I subtract the mean, and then I divide by the standard deviation of xtrain, again, axis equals 0 for the same reason. And then I can put that into parentheses, or actually, let's just keep it like this. And you can see we have the exact same values. So maybe I can collapse that a little bit. And you can see I have 81176, 81176, 369, 369, and so on. So this right here is exactly what the standard scaler does. If you want to do it manually, it just scales the data, it zero centers the data, and it makes it have a unit variance. Alternatively, you can also do min-max scaling, also quite simple. You just say from Scikit-Learn.preprocessing import min-max scaler, and same idea as before, scaler equals min-max scaler, and then again, x train scaled. Actually, let me just copy this. Is going to be the exact same code as before. Train scaled and test scaled is just going to be fit transform and transform of the data, but this time we have a different scale. We don't have any negative values. We have only 0 up until 1, 0 being the smallest value and 1 being the maximum value. So you basically press all the values to be between 0 and 1. That is also something that you can do. If you want to do this manually, again, in NumPy, it would look like this. You would first get the min and the max for the x value. So you would say np min x train per feature again. So axis is equal to 0. Same thing with max, np max. And then the calculation would be you take the training data, you subtract the minimum, and you divide by the maximum minus the minimum. And that gives us the same data that the min-max scaler gives us. So yeah, these are just two examples. You can decide which one you want to use depending on the use case, depending on the circumstance, but scaling your data is a must for certain algorithms. We're going to briefly touch on that when we get to the classification and regression models or algorithms. But essentially, if something is distance-based, like a k-neighbors classifier, like linear regression, anything also with a distance-based penalty, this is scale sensitive. Something that is based on threshold values like a random forest classifier or a decision tree classifier is not scale sensitive. Scaling doesn't really need to happen if you want to use something like this, but also oftentimes it doesn't hurt to scale anyway, so you can just always scale by default. Now let's move on to something else in pre-processing. We don't only want to scale the data, sometimes we need to encode the data. So some data gives us features, or some data sets have features that are not numerical features. For example, I can say here from Scikit-Learn.Datasets import, and now we have the function that I talked about, fetch OpenML. This allows us to load datasets from OpenML. Also, I'm going to say from Scikit-Learn.Preprocessing, we're going to take a look at the so-called ordinal encoder. I'm going to talk about this here in a second, but we can start by getting the data. The data is fetch OpenML. The dataset is the car dataset. I want to get it as a data frame, and I want to get the data frame itself. Now, taking a look at this, you can see we have some features that are, or actually all of these features are not numerical. We have here V high, low, or V high for very high. We have here some numbers, but here 5 more, or more than 5, I guess. Here we have small, medium, big. We have low, medium, high, and we have the class PN. So this is data that you cannot just feed into something like a k-neighbors classifier, because most, or actually all machine learning algorithms work with numbers, be it a neural network, be it k-neighbors classifier, be it naive Bayes. You basically have to have numbers to work with. And because of that, you need to take some of the features and turn them into numerical features, but you need to do that in a reasonable way. So I actually have, I think, a video on this channel where I go into detail on the different methods to encode features. You might want to take a look at that if you want to, if you're interested in that. But the short version is, for example, since we have here a feature that is on a scale, so we have small, medium, big, which is like an escalation. We have something that is on a spectrum. It's not something like color, where you have blue, green, and yellow. Of course, you could say color is also on a spectrum, but or countries maybe is a good example. You don't have something like USA, France and India, for example, but you have something where there is a progression, low, medium, high. In this case, it makes sense to just do an ordinal encoder to say, okay, this is just 1, 2, 3, because now we can work with these numbers and they're on a spectrum, which wouldn't make necessarily sense in terms of countries, because if you just assign numbers to countries, then there might be a scale that is being interpreted by the model that says, okay, the larger this value is, the more something. In this case, it doesn't make a lot of sense. So yeah, for these two, let's go with luck boot and with safety, and let's try to encode them here using an ordinal encoder. How would we do that in Scikit-Learn? We could define the columns to be encoded. Columns to encode are, as we said, luck boot and safety. So these are the two columns, and now I can create an instance of the ordinal encoder. I can say encoder is equal to ordinal encoder, and here I can pass some parameters. I can say categories is equal to, then a list of lists, and the first list here is for our luck boot, which is small, med, and big. Small, med, big, comma, and then a new line here, which is low, medium, high. Low, medium, high. And this is of course important because we want to have specific assignments here. I don't want to just do it in the order of appearance here, because maybe high appears as the first value, then low, then medium, and then I don't want to have 0, 1, 2 in this order. I want to actually have the order low, medium, high, 0, 1, 2, 0, 1, 2 also for small, medium, and big. And the encoding is quite simple. I just say now data columns to encode. So data is my data frame here. Columns to encode is equal to encoder fit transform, and then I can just transform the columns to encode. And then when I take a look at data, you can see now we have numbers here that we can feed into a machine learning algorithm. And of course, we can do the same thing for the other features as well. The cool thing is we can also inverse transform. So I can go ahead and say encoder inverse transform, data columns to be encoded, or columns to encode. And then it does the opposite. So it turns them back into what they were initially. So this is all stored in the encoder based on the categories here. Now, as we already said, some features should not be encoded using just numbers like this. Some features are a little bit more sophisticated. Country is a good example. Occupation is another one. And for those, we want to use something called a one-hot encoder. So a one-hot encoder is essentially something that turns multiple values for an individual feature into multiple columns that can be 0 or 1. Let's take a look at that. I'm going to go with a data set here. Let's say data is equal to fetch OpenML. We're going to go with the adult data set as frame. And this data set here is, I don't even know what the data set is, to be honest, but it has some columns here like occupation or race or maybe country here. So native country, race, and occupation would be perfect examples. Education, maybe not, because education is on a spectrum. Education can be encoded with ordinal encoder because there is a progression. There's lower education and higher education. In the case of occupation, race, and native country, that's not really the case. So these are now categorical attributes where there is no progression. There is no higher or lower. And because of that, it makes sense to use a one-hot encoder. So we're going to go and say now from Scikit-Learn.preprocessing import one-hot encoder. So let me scroll down a little bit. There's some bug here. There you go. Let's create a new cell down below. And with this one-hot encoder, our goal is now to take something like occupation, and instead of having a column occupation with all these values, or instead of having an occupation columns with numbers that represent these values, what we want to do is we want to have multiple columns for the individual values that we have here. For example, exec managerial, handlers, cleaners, profession, specialty, or whatever. And we have these individual columns, and they can be 0 or 1. So this makes sense because if you don't have too many individual values that are possible, this is much easier to handle, especially for something like a decision tree that has to just say yes, no all the time. So we can use perfectly one-hot encoder for that. So let's go and say data occupation value counts. And this gives us now a list of the different values that we have here and also how often they occur. We don't have too many different occupations here, which is perfect. So now we can take that and turn it into multiple columns. For this, I'm going to say import pandas as PD. And then I'm going to say encoder is equal to 1 hot encoder. Handle unknown is ignore. The idea of handle unknown is what if I get some value later on that I don't know about, so that was not part of the training data, then just ignore it, don't handle it. And then I'm going to say sparse is equal to false, so that we actually get the individual columns. And now I can say encoded values is equal to encoder fit transform and then data. I can do that for occupation and race, for example. Let's do 2 columns at once. And then I'm going to say new columns is equal to encoder get feature names out. So the reasoning behind this is I'm going to get the values, but I also need column values or column names. So I'm going to say now occupation, sales, occupation, armed forces. These are going to be the new column names. And this is what I get here with the get feature names out method. So I'm just going to pass here occupation and race again. You can take a look at that. I have a problem. Sparse is false. Probably it's sparse output like this. Oh, actually I only need 1 set of square brackets here. And now we can take a look at that. Encoded values is just zeros and ones. And if I take a look at new columns, you can see we have occupation, craft repair, occupation tech support, and so on. And we also have race Asian, race black, race other, race white as individual columns that can be 0 or 1. So if someone before was, let's say, race white, now they don't have a race column with white. They have a race, they have these individual race columns. All of them are going to be 0, except for white is going to be 1 because that person has race white. That is the idea here. Now, how do we actually take this and merge this together? We say df encoded is equal to pd data frame encoded values columns is equal to new columns. Index is equal to data index. So from before, the original data frame, we want to have the same index. And then we're just going to merge on this index. So we're going to say data final is equal to pd concat. And we're going to concatenate here data. So the original data frame, and we're going to drop the 2 columns here. So we're going to drop the... do I actually do this as a list? I think so, right? Occupation and race. So we drop that and we merge this together with the encoded data frame on axis 1. Or I'm just going to say columns is equal to occupation race, like this. Data final is now this. We don't have race anymore. We don't have occupation anymore, but we do have a bunch of occupation columns and a bunch of race columns here that are mostly 0, but some of them are 1. This is the actual value. And this is how we would encode something like this, something categorical that is not on a scale. And of course, I actually already showed you that you have much more stuff that you can do here. You can normalize, you can encode in different ways. You can use something like polynomial features to make something, to make linear features polynomial. And there's much more you can explore here. If you want to go deeper, just go to documentation and check out the individual classes and functions here. Now, once we have our data loaded, split, and pre-processed, we get to the actual machine learning part, and we're going to start by talking about classification. So for this here, let me just briefly replace the iris dataset with the breast cancer dataset, and also let me copy paste the steps that we already talked about. So just taking XY here from the load function, splitting it using the train test split, scaling the training and the testing data using a standard scaler. Everything we already talked about, quite simple. And now we actually want to train a classifier. We want to make predictions. What does it mean to train a classifier? In our case here now, we have a data set, 30 features, parameters, textures, sizes, radius, and so on. And we want to determine the tumor that we're seeing, the tumor that we're looking at in terms of the information and numbers here. What is it? Is it malignant or benign? This is what we want to train a model to predict or to classify or to detect or determine, whatever. And we want to do that with a high level of accuracy. So in order to do that, the concept is always the same no matter what you use, no matter what classifier, what algorithm you use. the code is always the same. You import a classifier, for example, let's go from Scikit-Learn, and then the one we already used, from neighbors, we're going to import the kneighbors classifier. All we have to do is we have to create an instance. So CLF is equal to kneighbors classifier like this. And then we just say clf.fit to train the model on the training data, in our case, the scaled training data. And the ytrain data, we fit the model is now trained. In the case of kneighbors classifier, it goes very quickly because we're just taking the data and that is the training in and of itself. But then I can evaluate the model. I can say classifier score, how well does the model perform on the unseen testing data. In this case now 96.49% accuracy. And now what I can do is I can just use this classifier to make predictions on individual instances. So I can say here's single instance. Let's say this is a new instance. Let's take it from the test data set. I can just say xtest0. Now the single instance looks like this. I just have the 30 values. Now I want to know, okay, what is the classification from my model? What does the model think that this tumor is, malignant or benign? So I can say here CLF predict. I have to pass a list because we usually pass multiple instances, and then just a single instance. And as a result, I get 0, which is, as far as I remember, malignant. So that would be malignant. That would be a malignant classification here. Whether it's correct or not, we can check by saying ytrain 0. And in this case, it's 1. So that would be a wrong, ytest. Okay, that would still be a wrong classification because ytest 0 is 1. We can try now with index 1 and we can get a 0 here. Now we can try, okay, wrong again. I can try here with index 2. Okay, so actually you can see that the classification is always wrong. The reason for that is we're not using the scaled testing data. That is why it classified it incorrectly. So if I say xtest scaled 0, then I get the scaled data. This is what the model is trained on. So pay attention when you're coding. This is something very important. You cannot just use the test data because it operates on a different scale. This is the proper data that we want to use. So now I make the prediction. Now I get 1. Now I can do it for something else. And I get 1. There you go. So now this aligns. This is how you do the predictions. Now, what model you use doesn't really change how you do this. You always fit, you always score for evaluation, or you use metrics, which we're going to talk about here in a second. And you always predict. Now, there's also a second function that you can use. I'm not sure if it's supported. I don't think it's supported by all of the different classifiers. But there's also a predict prop a function, so a predict probability function. What this basically does is it doesn't just give you the prediction, it gives you probability. So in this case, it says 20% 0 and 80% 1. This is just a measure of certainty here. That is also something that you can do, but the principle is the same. No matter if I use a kneighbors classifier or, for example, from Scikit-Learn.linear model, a logistic regression. Now, even though it's called regression, it's not actually a regression, it's a classification. The mechanism behind the scenes is regression. I have a very detailed video on this channel if you want to check it out for both of them. Actually, I have a kneighbors classifier from scratch and logistic regression from scratch video where we go through the mathematics and everything. But essentially, this is also a classification algorithm, and I can just easily swap it. I can say logistic regression, and the rest of the code stays the same. Nothing changes. I can use it as before. Same thing with, for example, Scikit-Learn.tree, import decision tree classifier. All I have to do is I have to change decision tree, and the rest stays the same. Then I can do something like a support vector classifier. So from Scikit-Learn SVM, use the SVC class. Same thing, replace, and just run. Okay, SVC doesn't have a predict probability function, so in this case, that does not work. Then we have from Scikit-Learn.ensemble, we can go with a random forest classifier. This is usually the strongest one. The strongest algorithm from the traditional ones most of the time. So random forest classifier. In this case, actually, it doesn't perform as well as the logistic regression, which is interesting. But the basic idea is you just do it like that. You can also go with one more. Let's go with a naive Bayes. I also have a video on this one if you're interested. Gaussian naive Bayes. just like this, Gaussian naive Bayes. And of course, they do differ. They do differ in their concepts behind the scenes, and they also differ in their hyperparameters. For example, if I go with a random forest, I do have some parameters here, like n estimators. How many decision trees do I want to use in my random forest? Now, a random forest is a collection of decision trees, so here I have a hyperparameter for that. When I take a look at the k nearest neighbors, I can set k, so I can set the number of neighbors to look at. So depending on what algorithm you're using, you can tune different hyperparameters. This is important if you want to optimize. And it's also important to know what you're working with, because some of them are scale sensitive, some of them are not scale sensitive. For example, k-neighbors, as we discussed, logistic regression, support vector machines, with the support vectors, obviously, they are all based on distance measures, which means that they're scale sensitive, which means that you want to scale the data before you use these classifiers. Whereas something like a decision tree classifier, a random forest classifier, or a Gaussian naive Bayes are not scale sensitive, because here we just do decision trees, we just do left-right decisions, and here we do essentially just Bayes rule or Bayes theorem. So because of that, we don't really need to scale the data. It doesn't harm us to scale the data, but you don't have to. So you should always know what you're working with, and you should always try different algorithms. Let's also take a look at regression now. For this, I'm going to fetch the California housing data set. And again, I'm going to copy paste the whole pre-processing stuff, same as before, exact same code as before. We just have XY, fetch California housing, train test split, scaling, that's it. And now the same principle here. The only difference between classification and regression is in classification, you're predicting classes. So either yes or no, or maybe also multiple classes. So you could have something like, what kind of animal is this? Cat, dog, horse, deer, whatever. That would be classification. Regression is on a continuous spectrum. So there's not classes, but regression would be something like, what is the price of this house? And then you can have a number like 1,528.64. That would be a regression task, because that is not a discrete value that you have as a class. It's not a label. It's on a spectrum, and you try to find the correct value on this numerical scale. So here we have a bunch of algorithms. The most well-known one is linear regression, I think. So from Scikit-Learn, linear model, import linear regression, the classic linear regression. We can say here rec is equal to linear regression, rec.fit, x train scaled, y train, that trains the model. Again, now I can say score on the test data, the scale test data. There you go. In this case, just now, don't be confused by that. This is not accuracy. This is not 57% accuracy. This here is the R squared. Where's my alt key? The R squared score. This is different. We're going to talk about this when we go to the metrics. We're actually not going to talk about this in detail. I do have on this channel a video on evaluation metrics for classification and regression, but this is basically how much of the variance is explained by the model, and in this case, just 57%. So you can treat it a little bit like accuracy. It goes from 0 to 1, but it's not really telling you how well the model performs necessarily. But that's the basic idea. And here again, I can say single instance is equal to, and then what was it? X test scaled 0. Then I can take a look at that. So I have the features here scaled, and now I can say regression or regressor predict single instance, and I will get some numerical value as a result. And again, this will not change. You create a regressor, you fit, you score, you predict. You don't have a predict probability because you don't have classes here, but that is the same idea all the time. And here you have different forms of regression. You have the lasso regression, you have the rich regression, you have a combination of the two, which is the elastic net regression. These are just regularizations that you add on top of the linear regression. You have also all the different stuff that we had before, like neighbors, like k-nearest neighbors. You have k-neighbors regressor as well, which uses the principle of k-nearest neighbors for regression. You have also, for support vector machines, an SVR, a support vector regressor. You have from ensemble, you have the random forest regressor, which is oftentimes very powerful. You also have from tree, the decision tree regressor. But the idea is always the same. The idea in terms of the code is always the same. You choose a model, you create an instance of it, you fit, you score, you predict. That is what you do. Again, I don't really want to talk about the individual methods and how they work because each of them deserves a video on their own. I already have a video on linear regression in detail. And if you're interested in any of these specifically, let me know in the comment section down below. I can make a video on individual methods. But in this crash course, I don't think it makes a lot of sense to cover linear regression or k-nearest neighbors or support vector machines. I do have videos where I do that. You can watch them if you want to go into more details. I just want to show you how to use these methods in Scikit-Learn. Now, up until this point, we only focused on supervised learning, which means we had data sets where we had some input data and some output data that is a ground truth, the correct response, so to say. So we had, for example, sizes and textures of tumors, and they were either malignant or benign. There was a true answer. Or we had some dimensions of a flower, and they were either this species or this one. There was a true answer. Now we're going to talk about unsupervised learning. Specifically, we're going to talk about clustering. And the idea of clustering is you have data. The data is unlabeled. You don't have any classes or something like that. And you want to cluster the data into reasonable clusters. That is the idea. And we can do that with something called k-means clustering, for example. So I can say here from Scikit-Learn datasets. Now we're going to use one of these generation functions, so make blobs that we talked about in the beginning already, or in the dataset section. And then I'm also going to say from Scikit-Learn dot cluster import k-means. And also, of course, we need from sklearn preprocessing the standard scaler. We don't really need to do a train test split here because we don't have any ground truth to train on. We don't have a true answer that we can teach the model. So we can just use all of the data for the clustering. And let's get the data. I'm going to say X and then just underscore because we're not interested in the classes. I'm going to generate the blobs, but I'm not going to actually use the labels. So I'm going to treat it as unlabeled data, even though the make blobs function actually returns the label as well. So we're going to say here, make blobs n samples. Let's go with 5,000. Let's say centers are going to be 5 different centers. And let's maybe use a random state here, 10, to always get the same data. By the way, you can use random state. I didn't mention that. You can use random state in a bunch of different functions. You can use it in train test split. You can use it in random forest. Everywhere in Scikit-Learn where you have randomness, you can say random state equals. And when you do random state equals something in train test split, for example, you're always going to get the exact same split. You're not going to get a different split every time you run the cell, which is what you get by default if you don't provide a random state. So we say X and nothing equals make blobs. We can take a look at that. This is what it looks like. Now we can create a scalar. Scalar is equal to a standard scalar. And then we say X scaled is equal to scalar fit transform X. And now we can just use matplotlib import matplotlib.pyplot as plt. And now I can say plt.scatter. And I can say x scaled everything feature 1, x scaled everything feature 2. And we don't need a color, so we get the unlabeled data. This is what it looks like. Now, this is the data set, and we don't know what the clusters are. Now, obviously, since we artificially generated a blobs data set, obviously, these are the 5 different clusters here. But this can be much more noisy. This can be much more confusing. And there's also not really a true answer. There's a more high quality answer. There's certain metrics that you can use. I also have a video on this channel if you're interested in that. But yeah, how do we actually now use an algorithm to determine the clusters? And of course, this is not so interesting in 2 dimensions because I can just do this by hand here. But oftentimes you have data that is 100 dimensional and you still want to find clusters. There you cannot just do it with your eyes. You need to use some algorithms, and you can still use the same method of k-means in 100 dimensions as well. So we can say here k-means, let me zoom in a little bit. k-means is equal to k-means. We provide here the number of clusters. So n clusters is something that we need to hard code. We need to provide it. We need to say I'm looking for 5 clusters. And then I say k-means fit onto the scaled x data. And as a result, what I can do now is I can get from k-means the labels. So I can actually copy the scatter function here, and I can say C is equal to k-means dot labels underscore underscore, because in Scikit-Learn, underscore indicates this is a trained parameter or something that is trained. And now you can see this is the clustering that we end up with. Now, I'm not sure if that is actually true. We can actually see if something changes. If I change this to Y and I try to visualize that. So if I say not k-means labels, but Y, then maybe we get a different color, not sure. I mean, we do get a different coloring. We don't get necessarily different assignments. But actually we do also have a difference. So if you look at these 2 points, in this case now they belong here. And in reality, they belong to the lower class here, to the lower blob. So this is incorrectly, if you want to call it that. But with clustering, it's more about recognizing distinct groups rather than trying to find the truth. So yeah, clustering is a different use case. But another thing that I want to show you is a clustering method called dbScan, which is more useful if you try to do something like a moons dataset. So if I say from sklearn.datasets import make moons, then I can say x, and again, no data, is equal to make moons. Make moons, let's go with and samples 5,000, and then let's go with noise 0.08 maybe. Then if I do the same thing here, so if I use the scatter method to just display it, actually, this is not, oh, I need to do the scaling again. So let me just copy paste this as well. Then you can see we have one cluster, so to say, here and one cluster here. Maybe I can also decrease the noise a little bit so you can see that more clearly. There you go. You can see this is obviously a cluster and this is obviously a cluster. Now with k-means, you're not going to get the results that you're expecting or that you want. So if I say k-means is equal to that, even if I set this to 2 now, let me just do this again. If I set this to 2, so now I'm looking for 2 clusters in this data, and now I want to visualize that again with k-means dot labels. Then you can see I get a split like this, because this is how k-means works. It just works with the Euclidean distance. Something like dbScan, on the other hand, is probably going to be able to handle that. So now I can try something else. I can say, instead of using k-means, say from scikit-learn dot cluster import dbScan, and then I can say dbScan is equal to dbScan. I provide an epsilon value for the distance. Let's go with 0.2. Again, not going into the details of the individual methods, just showing you how to use them and how they can get you different results. Doing this on x scaled again, and then basically doing here not k-means, but dbScan labels. And now you can see we have a proper clustering, a better clustering. And as always, if you are interested in more clustering methods, you can go to documentation, sklearn.cluster, and you can check out the different methods that you have here. Now, another method or another technique that belongs to unsupervised learning, but is also a sort of pre-processing technique, is PCA, so Principal Component Analysis. The in a nutshell explanation of PCA is you take a high dimensional data set, maybe you have 1,000 features, for example, and you want to reduce dimensionality, so you want to end up with 20 or 30 features, for example. What you do is you go into this n-dimensional space and you try to find the directions in this space. These are not necessarily features. They can also be new directions, so combinations of directions. And you find the directions, the 10, 20, 30 directions that explain the most variance, and you reduce your data set down to these directions. I hope this was not too confusing in terms of the explanation, but this can be used, for example, as a pre-processing step to reduce complexity or dimensionality before doing something else. I'm going to copy paste an example here for this. So I'm going to show you the steps that we already know. Here we import from Datasets, again, OpenML. We use a logistic regression classifier. We do a train test split. And I also have here now from Scikit-Learn.decomposition import PCA. So we're importing PCA from Scikit-Learn. And now we do what we already know. So we take this, we say, get the MNIST 784 dataset. Now, what is the MNIST 784 dataset? This is a handwritten digits dataset. So we have 784 pixels. I think it's 28 times 28. Does this make sense? Is this the dimensionality? Yeah, I think so. So 28 times 28 pixels. And each pixel is an activation value. So each pixel is a feature. So we have 784 features to predict 1 out of 10 classes. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Now, this is the data set. And of course, we can go ahead and now just train a logistic regression classifier. But what we can also do is we can reduce the dimensionality with PCA. Before we do that, we can also see that there is going to be a loss. So an information loss, a loss in performance. But you can decide how many components you want to use. And you can see how much this affects your actual performance. So what I'm going to do now is I'm going to say PCA is equal to PCA. I'm going to say I want to reduce this down to 10 principal components. So I want to have 10 features in the end, 10 directions. And then I'm going to say xtrain reduced is equal to PCA fit transform xtrain. And then also the same thing for xtest. And of course, again, not fitting, but just transforming. Okay, I think I didn't run the cell above, so it's using the old data set. Let me try again. There you go. Now it worked. So we have 10 principal components. If we take a look at xtrain shape, you can see we have 56,000 instances with 784 features. If I now go xtrain reduced shape, you can see we have only 10 features. All right, and what we can do now is we can just do a logistic regression classifier. So I'm just going to copy paste this because we already talked about this, creating a classifier, limiting the number of iterations in this case to not have this run too long, fitting the data set onto the training data and evaluating it onto the testing data. In this case, I know I didn't scale, so that is, of course, something that should be done as well with logistic regression since it's scale sensitive as well. But in this case, we just don't do it. We get a performance here of 91, so 0.9172. And now I can do the same thing with the reduced data. So reduced. And we can see how much worse this performs when we reduce the data from 784 to 10, and we still get 80% accuracy. Now, if I increase this, for example, to 20, this should give me better performance. There you go, I get 87. So this is still better. You can also see, I'm not sure if I'm going to cut this, but this was also a bit faster than this above. And that is the reasoning. You want to reduce noise, you want to speed this up. This is something that you can do with PCA as a pre-processing step to reduce the dimensionality of your data. And you can also see how much variance each direction explains. So I can say here PCA dot explained variance ratio, and you can see that 0.09% of the variance, so this portion of the variance here is explained by the first direction, and then you can see the other directions as well. You can also say NP sum and see that the total amount of variance explained by our directions is 0.64. Now let us move on to the metrics module of Scikit-Learn. How can we evaluate our classifiers and our regressors? For this, I have prepared some code here that you should already understand. Nothing new. We just load the breast cancer dataset. We do a train test split. We create a scaler. We scale the data, and then we train a k-neighbors classifier. Now, of course, what we can do is we can just score as we did before, clf.score, xtest scaled, and then ytest. This is how we did it before. This gives us the accuracy. We can note this down. We can say this is the accuracy score. But that is just one metric that we could be interested in. We could also be interested in precision, for example, or recall. Now, precision is not the accuracy. The accuracy tells us out of the examples that I wanted to classify, how many did I classify correctly? Precision tells us when I say that something is true, so when I give you a positive instance, a 1, how often am I correct? And recall would be something like, how many of the correct instances do I recognize? For example, if I always say yes, if I always say 1, if my classifier always predicts 1, it's going to have a recall of 100% because it's never going to miss a positive instance. If I only say yes once, so if I only say 1 a single time and I'm correct, and all the other times I say 0, no matter how wrong these zeros are, I'm going to have a precision of 100. Now, if you're interested in all these metrics, I have a video on this where I go into the details. For now, let's just take a look at how to use various metrics. We can say here from Scikit-Learn.metrics import, and we can import, for example, the accuracy score, or the precision score, or the recall score, or a combination of the two, the F1 score, which is balancing precision and recall, so both have to be at least not too low for the F1 score to not be too low. And all I have to do now to evaluate my classifier with these score functions is I have to say, give me the predictions that my model makes on the test data. So my prediction is equal to classifier predict x test, and then just feed in to a function, so accuracy score, for example, the correct classifications and the predictions of my model. So y test, y prediction gives me, of course, a very low score because we should not predict the test, but the test scaled data. And now we get the exact same number as here, 97.368%. And we can do the exact same thing with all the other scores. So I can say my precision, the precision of the model is just a result of feeding in the predictions. There you go, 97.297. Then the recall score of y test, y prediction is 98%. And then I can do F1 score on the same data, y test, y prediction, and I get 97.959. And you can do that with a bunch of different metrics. We're going to take a look at that here in the end, again, in the documentation. But of course, the same thing can also be done with regression. I have a similar setup here. I just import or load the California housing dataset. I do a train test split. I do scaling. I fit a linear regression model. And then, of course, I can do score again. So I can say rec score x train scaled and y train. This gives us, in this case, the R squared metric, or R squared score. But I can also go ahead and say from Scikit-Learn.metrics import, and I can do stuff like R2 score, so R squared score. I can also do mean absolute error, or mean squared error, or root mean squared error, for example, RMSE. So I could go ahead and say again, y prediction is equal to regressor predicting the x train scaled data, this time correctly. And then I could do R2 score, y test, and y prediction. And of course, I should be predicting the test data, not the train data. There you go. And also here to get the same number, of course, we should be evaluating the test data. There you go. Now we get the same number. The score method is just the R2 score, but I can also take a look at the mean absolute error of y test, y prediction. Then I get this. I can also do the same thing here with the mean squared error. And I can do the same thing with the root mean squared error. There you go. So that is what you can do with Scikit-Learn metrics. As always, there is a page for this. There is a documentation with all the different metrics that you could use for classification, for regression, for clustering. There's a lot to take a look at here. And again, I have two videos, one for classification, one for regression, where I explain the different evaluation metrics, when to use what, and what the nuances are. Now, if you want to see how well a model performs on your data, you don't necessarily have to split the data. You can also use something called cross-validation. The basic idea is you split your model up into folds, into sections, so to say, and you train on all but one section, and then you evaluate on the remaining section. And then what you do is you change the sections that you use. So for example, maybe let me use a comment for this. If I have section 1, 2, 3, 4, 5, these are just portions of the data. Let's say each of them have 100 instances. What I would do is I would train on these 4, evaluate on this one. Then I would train on these 4, evaluate on this one. Then I would train on this and on these and evaluate on this one. That is the idea of cross-validation. By doing that, I don't have to use a training or testing set, and I can validate my model without having to do the split. So how do we do that? Again, what I have here is just loading a data set and creating a scalar, scaling my data. And now what I can do is I can say from Scikit-Learn dot model selection import cross-val score. So this allows me to cross-validate the model. I can create a classifier, a k-neighbors classifier, and I can say now scores is equal to classifier to cross-val score given the classifier, given the scaled data, given the ground truth, and using 5 folds. By doing that, I get 5 different scores, and then I can take the average if I want to. I can say import numpy SNP, NP mean scores, if I'm interested in that, and then I can get the average performance here. This is also a way to do validation, and this doesn't have to be done just with accuracy. I can also do the same thing by providing a different metric. So I can say scoring, for example, is equal to precision, and then I would do cross-validation based on the precision metric. And now this concept of cross-validation can also be used to do something called hyperparameter tuning, which means optimizing our model, because every algorithm, every model that we use has certain hyperparameters that we can tweak to hopefully increase the performance. So if I go to the random forest classifier, you can see a bunch of parameters here that we can pass. We have some default values, but these of course can be changed. For example, in a random forest classifier, the number of decision trees in that forest, by default 100. Then also the criterion. We have the max depth of the forest. We have min sample split, which is the minimum number of samples required to split an internal node. And we have a bunch of other hyperparameters. And for example, for k-nearest neighbors, that would be the number of neighbors to look at. Every method, every algorithm has different hyperparameters, but essentially you can tweak these to hopefully get some better performance. And this is what we can do automatically with hyperparameter tuning. In the case of Scikit-Learn, we're going to use grid search, and you can also use randomized search, which is providing boundaries or providing ranges and then doing something randomly. We're going to focus on grid search in this video today. The basic idea is you define a parameter grid, so what you want to check, and then you just try and see what works best. So how can we do that? Let's start by importing a data set. I'm going to import again load breast cancer. I'm going to import random forest classifier. I'm going to load the data and do a train test split. For this, of course, I need to also import the train test split. And we don't need to scale because a random forest classifier is not scale sensitive, so we can just leave it like this. And now what I do is I define a parameter grid. I define what kind of hyperparameters do I want to check out. And for example, I could say for n estimators, for the number of trees to be used, I will try something below the default and something above the default, for example. Maybe we can even go to 200 here. Then for the, min sample split, what is the default there? I think it was 2, if I'm not mistaken. Min sample split is 2. So what we could try here is we could say 2 or 5, just 2 different values. And then we could try something like the max depth of the tree, of each tree. What we can do here is we have no limit, we have 5 and we have 10. I think the default is none. So we can try to limit the tree. And this is now what is going to be tried. Now you need to understand that all of this is a combination. So what grid search is going to do now is it's going to try this, then it's going to try this and this. So the first configuration will be 50 estimators, no depth limit, 2 as a min sample split. Then it will go and say 50 estimators, no limit, 5 min sample split. So it's going to try all the combinations. So in this case, 3 times 3 times 2. So in this case, 9 times 2 is 18 different configurations. And it's going to give us the best configuration based on the cross-validation. So we're going to say classifier is a random forest classifier. I'm going to provide njobs -1. This just means use all the CPU cores. Don't just limit yourself to a single core. And then I'm going to say here, grid is equal to, of course, I need to import this first. So from Scikit-Learn dot model selection import grid search cross-validation. Grid search cross-validation. I'm providing the classifier, I'm providing the parameter grid, and I'm providing the K for the K-fold cross-validation. So how many folds do I want to have? Let's go with 5. What this basically means is I'm going to do everything 5 times, which means 18 times 5. So this is quite, actually let's go with 3 to not have this take too long. Now 18 times 3 should be manageable. I can just create this, and now I can say grid.fit xtrain ytrain. And we don't need a testing set here. We don't need a validation set here, because all it's going to do is it's going to do the cross-validation to determine which one is the most effective. And now it's done. So I can say grid.best params. And the best params are no limit, min sample split 2, estimator is 100. Okay, these are the defaults. It's not always going to be the case that the defaults are the best. Sometimes that is not the case. If you find, for example, that something like 200 is better, I would go even further, try 300 to see if it works better. In this case, just the default seems to be the best. And you can also get the best classifier by saying grid.best estimator. This is going to return the random forest classifier with the optimal parameters. And now what you can do is you can evaluate that by saying best classifier score X-test and Y-test. This is something you need to understand. Sometimes we have validation sets as well. Validation sets are used for hyperparameter tuning. Testing sets are never used for tuning hyperparameters. Testing sets are used in the very end to check if the model that you're comfortable launching is actually performing well on unseen data. You don't try to improve your model based on testing data, because that would skew the results and you have nothing to finally test on again. And then the last concept I want to cover in this video today is the pipeline. So let's say we have a data set here. We want to start by scaling the data. Then we want to reduce dimensionality with PCA. And then we want to train a random forest classifier. Instead of doing this one by one manually, we can also use a pipeline. So I can run this here, the basic train test split. And now I can say from sklearn.pipeline import pipeline. And I can create this pipeline that does exactly what I said in a row. So pipe is equal to pipeline, and then I can pass a list. The first thing I want to do with the data as it comes in is scaling. So I'm going to say scale. This is just the name here. And what happens here is a standard scaler, quite simple. Then I want to say PCA. I want to do dimensionality reduction. So PCA to 10 components. The breast cancer dataset has 30 features, so that is a reduction in dimensionality. And finally, I want to do random forest. So let's say forest, random forest classifier, like this. And that is now a pipeline. Instead of doing scalar fit transform, instead of doing PCA fit transform, and then fit and everything here with the random forest classifier, I can just say pipe fit xtrain ytrain, and then you can see this is executed together. And then I can also say pipe score X-test Y-test. So I can do everything in a row, and I get 91.6% accuracy. This is just a more convenient way to do this all in one, instead of doing it one after the other. So that's it for today's video. I hope you enjoyed it and hope you learned something. If so, let me know by hitting the like button and leaving a comment in the comment section down below. Also, let me know if you want to see more crash courses, what kind of crash courses you want to see. I already have NumPy, Pandas, Matplotlib, and so on. Let me know what you're also interested in. Let me know also if you're interested in a more advanced Scikit-Learn course where we go into more details. There's a lot of things that I didn't cover in this tutorial yet. And also let me know if you want to see more machine learning content in general, maybe going into the theory. I also have these from scratch videos where I try to explain the maths and then implement everything from scratch in Python. So check out those if you want to. And besides that, of course, don't forget to subscribe and hit the notification bell to not miss a single future video for free. Other than that, thank you much for watching. See you in the next video, and bye.